If you'll recall, we were working and talking about Jane, who was shifted her interest from nuclear chemistry into fireworks. We mastered nomenclature at this point. We can talk about ionic, covalent, and organic compounds. So now we really need to start digging into some of the chemistry about why fireworks behave the way they do. And in particular, one of the cool things and one of the really important things about a really good fireworks show is color. We want to have really vibrant blues, greens, reds, yellows. We want white. We want different colors of light. And these are fireworks are all driven by chemical reactions, things burning for the most part. Okay? So what we need to do is we really need to understand how does light, how is light generated from chemical reactions? How does an atom emit light? And how can we look at the light emitted from an atom as a way to understand how its electrons are arranged and how electrons behave inside of atoms? Because that's really the focus here. The chemistry that we do is fundamentally about looking at how electrons behave inside of atoms and how that causes all the chemical properties that we typically want to deal with. Now, the development of this model is really dependent on the development of our understanding of light. Okay? So electromagnetic radiation can be thought of in a couple of different ways. Around the turn of the century, sort of really popular, really important ideas around this begin to be developed and become really crucial in understanding what's going on inside an atom, because light turns out to be a really good tool to probe how electrons are behaving inside of an atom. So we first think of light as a wave, okay? And as a wave, it has certain properties for the way that waves behave. And we think of light as what we call an electromagnetic wave. That is a wave oscillating in both an electric field and a magnetic field. And it is the interaction of the electric and the magnetic field, sort of force lines that we think about when we talk about light as a wave. That's sort of the classic idea, is this electric field and the magnetic field. When the electric field is strong, the magnetic field is weak. But the changing electric field generates a magnetic field, and the changing magnetic field generates an electric field. This self-propagating nature of light, the fact that it is a self-propagating wave, is really what turns out to be sort of unique and what drives a lot of our understanding of the way that light behaves. Okay? There's this fundamental dichotomy, however, between this light as a wave phenomenon, okay, and light as a particle, which we'll talk about in a minute. Now, one of the sort of important factors here, one of the important concepts around a wave, is that in our experience, most waves travel in a medium. Right now, I am using sound waves to talk to you, okay? I have in my throat vocal cords that are vibrating. They are causing vibrations in the air, pressure waves, areas of high pressure and low pressure, that your ears have a membrane that vibrates with that change in pressure. And that's what you interpret as sound. We've all seen water waves. If you drop a drop into a cup, you can see ripples, or on a pond, that typical picture of ripples spreading out in a pond. Ocean waves, if you go down to the beach, you can see the ocean waves coming in row after row of these repeating waves. All of those things have one thing in common. They travel through some medium. Without air, without a gas, or some sort of solid, or even a liquid or solid, you can't have sound waves, right? Nobody can hear you scream in space because there's no air, there's no sound, so you can't transmit that kind of pressure wave. Water waves, ocean waves, ripples on a pond, they all need water. If the water's not there, you can't transmit that wave. Earthquakes, they've got to have the land, the solid land that pressure wave that is the earthquake travels through. You have to have a medium. So for a long time, everybody said, all right, light behaves at a wave. It's got same kind of properties. It behaves in many ways the same as water waves or sound waves. It's got to have some medium that it travels through. Okay, because it's a wave, and waves have medium that they travel through. And so what everybody said was, okay, well, the medium that it travels through is the ether. Okay, this is this sort of, we can't detect it because the light travels through it, so it's not something we can see in that way. But the light has to have a medium. And so for a long time, a couple of guys, American physicists, Michelson and Morley in particular, did some of the seminal work on looking at how can we detect this ether? How can we detect this material that the light travels through? And so what they did is they did a seminal, a famous experiment where they used some light waves, okay, some lights, and they showed lights at right angles to each other and had them interfere, and they looked at what's called an interference pattern. Waves, when they come together, if you've ever seen two waves, like two drops of water in a pond or whatever, waves interfere and you get this particular kind of pattern. Depending on how the light is traveling on these paths, it goes out and bounces and comes back together. When it comes back together, if there's any difference in how it's traveled out and back, you'll see that difference in the interference pattern, the pattern of how the light interacts with itself. And so the idea here is that the Earth itself, since it's traveling around the sun, and the sun is traveling through the universe, must be moving through the ether. So if we look at different points in the year, if we take our apparatus and rotate it, we should see differences depending on whether one of the legs is going with the direction that the Earth is traveling, and one of them is at right angles, or if we turn that, if we change that, we should see changes in the interference pattern, depending on whether we're traveling with the ether or against it, or at right angles, okay, depending on the motion of the Earth as sort of the baseline here. And so they did a ton of research. They did many different experiments, trials. They took out as much of the error as they could. There were problems with trucks going by outside, causing disturbances in their apparatus. They mounted it in this enormous vat of mercury and floated in this huge granite block on a vat of mercury so that they could isolate this from vibrations around. And they did some exquisitely detailed and really careful measurements and found nothing. They could not detect the ether. Okay? So they figured that, well, they just needed more sensitive equipment. But other people began to believe that these experiments should have detected the ether, this substance that light travels through, if it exists. So maybe this substance doesn't exist. Maybe light is different and unique and behaves in its own special way. Okay? Maybe the light has other properties that aren't going to be like a normal wave. Sorry, that's just bugging me when it flies up. So, if there's no ether, if light can behave not like every other wave that we know, maybe it does other things that aren't like other waves that we know. Maybe it's sort of this really special category. And there's a lot of work that these ideas, this lack of the ether, begin to stimulate that as we begin to look in more detail about light. Okay? And the next sort of important step in the development of this idea of how does light behave is in the 1900s by a German physicist, Max Planck. And Planck is studying what's known as black body radiation. That is, you take a solid, dark-colored object and you heat it up, and it produces light. Okay? The hotter it gets, the color changes. Okay? And we've all, if you imagine, say, taking an iron bar, and you heat it up, and it changes color. Okay? Well, you can look at that light and try and mathematically model how it behaves. You want to mathematically predict what color you'll get at different temperatures. And so Planck is trying to do this, and he keeps running into problems. If light behaves as purely as a wave, if it's this continuous emission, the math doesn't work out. It doesn't match what we're seeing in reality. So Planck makes this sort of huge jump in understanding how light behaves. Okay? He gets this big idea. And it's interesting because a lot of this research is actually driven by ways to try and improve light bulbs. Because light bulbs are essentially black body radiators. We're just taking a little filament inside there and heating it up hot. They use different substances. Today we use tungsten inside the light bulb, an incandescent light bulb. That just gets hot. It's just heating it up, and that's what causes it to give off light. And so what the idea, the math that Planck comes up with is fundamentally different than people had previously viewed light. We had thought of light as this continuous emissions, continuous, just as we had talked about, when we talked about continuous matter, we said that doesn't work that way, there's little atoms. Well, Planck realizes that the math will only work out to describe what's happening if the energy emitted by a photon is quantized. That is, you can't have any energy of photon. That the energy has to come in specific bundles. That you don't have this continuous spectrum. That what you get is actually discrete bundles of energy that come to be called photons. So that's fundamentally different than a wave. When you have a water wave or you have a sound wave, it's not like a little bundle of energy. It's this continuous wave form. Okay? Now, Planck's equation basically says that the energy of the photon is equal to h, a special constant that Planck made up, so we call it Planck's constant, times v, the frequency of the light. Okay? So here we have energy is equal to hv. This isn't really v, it's actually nu. It's a Greek letter. It's kind of a squiggly v. And Planck's constant it's a really tiny number. So it's times 10 to the negative 19, 6.3 something times 10 to the negative 19. Frequency. Remember frequency? I mentioned that back on the first day of class. Frequency is how often something happens. So the frequency of a wave is how often does the wave cycle in a second. So if you imagine sitting on the pier, like the Berkeley Pier, and the waves are going by, every time a crest comes by, every time the top of a wave comes by, if you counted how many you have in a second, that would be the frequency of the waves. So how many waves do you have going by a given point in a second? So, still working with waves, but now we've sort of bundled them up. We have like a little packet of energy. That the waves have a discrete energy, and it's not continuous. There's actually some sort of specific distribution of energy that it has to have, limited by this equation. Well, this work turns out to be fundamentally important for stimulating another scientist, a guy you may have heard of, Albert Einstein, in trying to understand how light behaves. So Einstein is working on a whole bunch of different ideas. This is sort of Einstein's great year. He's working at the patent office, and he comes up with this revolution in physics. Pretty much, well, there's a lot of question as to how much his wife was involved in the work as well. She was a physicist too. She doesn't tend to get a lot of credit. However, he did give her his Nobel Prize. So, when they divorced. A lot of interesting interpersonal dynamics there. So, Einstein is working on the photoelectric effect, which is trying to understand how light interacts with matter. There are certain types of materials, in particular metals like selenium and other metals, where if you shine light on them, they emit electrons. So the light hits the metal and it kicks off electrons. And what's really interesting about this light to electron sort of transition is that there are some real interesting things here. It doesn't seem to matter as much how bright the light is as what color it has. And so there are a lot of really interesting trying to figure out what's going on in terms of, well, how do the electrons come off? How many come off? How does the light cause this to take place? And what kind of impact does that mean for this idea of light as a wave? But it seems to be acting a lot like a particle when this happens. And so what Einstein comes up with is a sort of fundamental relationship between the energy and the speed of the light. Okay? That there's this relationship that we saw before, but the thing that changes, the fundamental idea, is that the only way you can explain some of these behaviors is as if the light is acting as a particle. But the only way you can explain a bunch of the other properties of light is if it behaves as a wave. And so it's both, it's neither, it's weird and non-intuitive. This is one of those sort of critical non-intuitive moments in science where somebody, Einstein, makes this big leap and says, hey, it's this whole different thing that we've never really experienced before, that we don't see in our everyday lives. That it has wave characteristics and particle characteristics. You can only explain this photoelectric effect if you treat the light as a particle. And so Einstein comes up with an equation, or derived from this energy equation. This is the same equation. This is Planck's equation with Planck's constant right here. But we've converted this, instead of using the frequency, we're using the wavelength, which we could attribute to color of the light. Okay? That's a nice relationship here. And so c, the speed of the light, divided by lambda, the wavelength of the light, is the frequency. C is the speed of light. 3.0 times 10 to the 8th meters per second. I don't remember off the top of my head. It's been measured. It was measured several times, including early. You can do early measurements on light. I'm sure if you haven't, you should at some point do this sort of classic experiment where you go and you have like a friend go stand on the other side of a field. Like you go to a soccer field or a track, and you have them clap their hands, okay? And you'll see the clap, and then a beat later you'll hear it. And this is sort of the classic example that, the speed of sound versus the speed of light. And the same sort of thing when there's thunder and lightning, right? You have this, you see the flash, and then you can count and find out how far away it is based on the speed of the sound. And so there is a difference in the speed of light versus the speed of sound. And so that was sort of this sort of classic idea where you can start to try and measure those effects. The most accurate measurements of the speed of light, I think, are typically done by bouncing laser beams off the moon, that kind of stuff, right now. But there's a bunch of different ways that you can do it. But what's interesting and what Einstein realizes is that if you have this energy of a photon hitting this thing, that and the big leap of physics, of course, is this understanding that when we describe a photon as a particle, that there's this relationship between the energy it has and the mass that particle could be converted into. And so Einstein comes up with that, it's probably one of the most famous equations, right? E equals mc squared. So we have this relationship between energy and mass. And this all fundamentally comes from this idea of light, that wave-particle duality, stimulating an equivalence between energy and matter. that if it's a wave and a particle, well, particles have mass. Well, maybe this wave, this energy has a mass equivalent as well. And again, the leap here is, the non-intuitive is, well, maybe they're really just the same thing expressed in different ways. So, Einstein comes up with a whole bunch of this kind of stuff in around 1905. But this isn't the end of the story for our purposes. This is really just the beginning. This is all sort of background stuff. In 1913, a Danish physicist, Niels Bohr, puts together these ideas of quantized energy, but the photons have this special quantization. The work of guys like Bohr in looking at the spectrum of light emitted by, say, hydrogen, because hydrogen turns out to be really easy to study. And so if you look at this spectrum, right, we shine some white light through a prism, and we get this sort of rainbow pattern here. This is incandescent. This is our black body radiation. We have that nice, full, complete spectrum. Okay? But if we look at a gas emission tube, we take a single element and we get it to emit light. Okay? So, for example, this is a hydrogen one. Here's the hydrogen, the light from the hydrogen emission. Okay? When it shines on our screen, instead of getting just this nice continuous spectrum, what we end up getting is a few lines, a few bright lines. Okay? And so Bohr came up with a mathematical formula that you could use to relate these lines together. But he didn't understand why that was true. Okay? So we had this mathematics that could describe these particular lines. But it's Bohr that puts that idea together with this quantization idea and with ideas about electrons inside of atoms, okay, and their orbits. Remember the orbits idea from Rutherford? We had that idea of orbits. It's Bohr that puts this all together to explain why you get only particular colors of light emitted from hydrogen. The Bohr model is that there are only certain wavelengths, certain energies of light that are emitted because there are only certain energies that the electrons can have inside the atom. Instead of being able to orbit wherever it wants, electrons can only orbit, can only be in certain energies, certain distances from the nucleus. Bohr numbers those energies 1, 2, 3, 4, 5, so on, okay? And it comes up with the math that we can use to describe this, okay? We have an equation. He comes up with an equation to describe that energy that an electron has based on the energy level. How close to the nucleus are you? 1 being the closest you can get, 2 being the next closest, 3, 4, 5, and so on. And Z, the effective nuclear charge. Effective nuclear charge, effective charge in the nucleus. So for hydrogen, this Z is 1 because it has 1 proton. So, J is the units. That's the units of joules. That's our energy unit. Okay? So Z is the protons, the number of protons in the nucleus, basically. So for hydrogen, it's 1. N is the energy level, the principal energy level.
So how did you use Bohr's?
So here's the thing. The equation that describes these wavelengths is essentially, that math, this math, was really developed by Bohr. That equation that says, hey, it's got to vary by this number times 1 over some integer value n squared. what Bohr does is he explains why that equation must exist in terms of saying, hey, the reason why you can only have these certain energy levels is because those are the only energy levels that can exist inside the atom. Okay, so there's this leap from a law, an understanding of what's going on, to a type of explanation, to a deeper sort of theoretical understanding of, hey, what this means is that there must be some sort of constraints on where the electrons can be inside the atom. That's what Bohr does. He comes up and he says, hey, look, the only way this works is if there's only certain places that the electrons can be inside the atom. And that's a big change. It's a huge difference in how we view what's going on. He also continues on, as we'll talk about, to more fully flesh out and explain why that is. And it has to do with coming back to the wave characteristics. We talked about light having wave-particle duality. Well, it turns out that everything has this wave-particle duality, including you and me. But that we typically don't see it. It's not something that is visible or noticeable on large scales. So we'll talk more about that wave mechanics or quantum mechanics in the next few days. So you need to be able to use this equation with a z equals 1 for hydrogen. And you need to be able to calculate energies. This is pretty straightforward. You're just going to stick n values in here and calculate energies. So you can calculate the energy for an n equals 3 or third energy level and an n equals 2. N is what we call the energy level. And it represents you can think of it for now like the orbit that the electron has. The lowest orbit it can have is n equals 1. That's the closest to the nucleus that the electron can get. And it goes up from there, each one further and further away from the nucleus. Now, this idea of an orbit is old-fashioned and doesn't really explain what's going on. So take it with a grain of salt. I'm going to teach you a better reality or a better model in the next couple of days. Yes, there can be lots. Generally, you are either going to be given the n values in the problem, or you'll be given the energy and asked to find the n value. Right. There's two ways to do that.
What do we plug in for
J is not a variable, it's the units.
Okay.
It's like meters, except it's energy. Joules are the energy. So, question. Yeah, here's what I'd like you to do. I would like you to calculate the difference in energy to go from n equals 3 down to n equals 2. Okay, for hydrogen. We're going to stick with hydrogen right now because this equation only really works for hydrogen. Okay, light is emitted when an electron drops from a high energy level down to a lower energy level. And energy is absorbed, an electron has to gain energy to go from a low energy level up to a high. So what I'd like you to do is calculate how much energy is emitted, how much energy does a photon have when it drops from n equals 3 down to n equals 2. And there should be a box on the sheet that has an example space on it. Yep. With the equation right there.
I really like this.
I thought it was... should have something like negative 3 point something or other. 3.0. Yeah. Times 10 to the negative 19th joules. This negative sign means that the electron lost energy. This negative sign means that the electron lost energy. That's all it tells us. When we deal with energy, positive and negative simply tell us direction. Did it gain or lose energy?
And what is it measured in? What?
Joules. The units are joules. Joules are the measure of energy. Yeah, but these n values are exact. So it's really just this constant here that limits us. So to 4 sig figs. This is a measured value here, related to the Rydberg constant. So, all right. So the Bohr model is a type of calculation that we can do. It shows up very occasionally on the AP test. Haven't seen much on the IB test in my looking at old tests. I think it's 19th, but I haven't done the math myself. Most people get 19. Okay, so I'll double check it, but I'm pretty sure that sounds right. All right, looks like Jane is pretty set up here. She can get all the colors she wants because different elements will emit different colors of light. Okay? What we have here is a bunch of different metal salts. Okay, metal ionic compounds of different metals. And it's typically the metal that is going to be important here. And it's the metals we typically use in fireworks. So they're taking a little wire here, a platinum wire, and they're taking the metal and sticking it in there. Okay? So there's sodium acetate. And they're grabbing a little loop of copper chloride. It's the copper that gives us that nice blue color. Sure. Jane's experimenting. So boron gives us that green color, boric acid. So potassium chloride. You get a sort of faint purple blue color.
So what are these colors representing?
The colors represent the energy levels inside the atom. It's that transition between the energy levels that drives this colors. So lead. This is going to be, this is another copper compound. Yeah, copper 2. Get a nice green color.
So like what's the high?
Yeah, lithium, get that brick red color. So the high energy level colors, the high energy is going to be some series of 3, 4, 5, 6, something like that. And they're all going to be dropping down to energy level 2. Because energy level 2 drops from high energy levels down to energy level 2. That's where you get visible light. If you drop down to energy level 1, you end up getting ultraviolet light, which has more energy than visible light. And you're going to learn a lot more about these energy structures in the next couple of lectures. There's a reason why this isn't, I don't do this in class anymore. It's because vaporizing those metals is not good for us to breathe. So I showed the video instead of doing it. All right? Excellent.